Alright, today we are going to look at a couple of FRQ questions from our review for the quiz on Monday. So let's go ahead and take a look at what we've got here. It says, on a certain workday, the rate in tons per hour at which unprocessed gravel arrives at a gravel processing plant is modeled by that function right there, where T is measured in hours and hours is in from 0 to 8. So basically what they're saying here is that the plant that we're looking at is open for 8 hours out of the day. It says at the beginning of the workday, the plant has 500 tons of unprocessed gravel, and then during the hours of operation, the plant processes gravel at a constant rate of 100 tons per hour. Now, we did this one in class. Let me first fix that. We did this one in class, and so let's just go ahead and go through it rather quickly. The first thing I want to do is I want to go to my nifty TI Inspire right here, and I want to go ahead and input that function into the calculator. So you can do this a number of different ways. You can either graph the function, or you can use the storage option. It really doesn't matter. I'll go ahead and graph it. That way we can have it, because eventually I'm going to use the graph anyway. So 90 plus 45 cosine and notice how nothing appeared, but that's because it's outside of my window. It's because of that 90 vertical shift on the outside of the cosine, but we'll readjust the window in just a second. So I'm going to go and click this button again right here. So it's stored as my f1 of x. And so the first thing I want to do is I want to calculate g prime. And so let me go back to the question here. It says g prime of 5. So if I'm going to find g prime of 5, this is part A, g prime of 5, all I need to do is to go back to that nifty TI Inspire and then punch the stuff in. So just go to Menu, Calculus, Derivative at a point, because we're trying to find g prime at 5. So my value is going to be 5. And now you get this derivative sign with the option to put something in. So you can either re-put in the equation, or because you have the function already defined in f1, you're going to say f1 of x at x equals 5. You hit enter, you get this crazy thing, and you hit enter again, and you get negative 24.5875. So let's go ahead and throw that in there. So negative 24.588 is what I'll write down. Now, it also says to interpret the answer in the context of the problem. So in class, we came up with an explanation. I will go ahead and pause real quick and retype that out. Hold on, please. Cool. So there's my explanation that we had in class. The rate at which the gravel arrives is decreasing at 24.588 tons per hour. Now make sure you guys are being extra clear on this, because this typing option doesn't have the squared option. It's actually tons per hour squared when t equals 5. Okay, cool. So let's take a look at B. It says here, find the total amount of unprocessed gravel that arrives at the plant during the hours of operation. So if we just want to look at how many tons of gravel arrives, that's when we talk about total amount of unprocessed gravel. That sounds like total distance traveled on those particle problems. So hopefully it makes sense that we are going to integrate from 0 to 8, because those are the hours of operation. We're going to integrate the rate at which the gravel comes in, because by finding the area under that curve, we will find out how much gravel is coming in. So go back to your nifty TI Inspire here, and now I'm going to go ahead and use the integration function. You can either go to Menu, Calculus, Integral, or you can just, if you wanted to do a shortcut, you would just go Shift plus, and you'd go from 0 to 8 of f1 of x dx, and you hit enter, and you get 825.551. So now you go ahead and you put that into your answer. So that is 825.551 tons arrive in 8 hours. Part C is saying, is the amount of unprocessed gravel at the plant increasing or decreasing at time equals 5 hours? Show the work that leads to the answer. Okay, one thing we got to remember is that this function right here is the rate at which gravel is coming in to the plant. So if I wanted to find out how much gravel is coming in at the plant at time equals 5, really I really just want to evaluate what g of 5 is. So what you do is you go back to your Inspire and you hit F1 of 5 and you hit enter and you get your cool answer. So that is 98.141 tons. That's how many tons of gravel are coming in when time equals 5. Now the first instinct is to say, yes, of course it's increasing. This number is positive. Of course it is. But remember, the plant processes gravel at a rate of 100 tons per hour. So in the context of this problem, what's happening is 98.141 tons of gravel is coming in at time equals 5, and yet 100 tons is being processed and shipped out to Home Depot or wherever it is it goes. And so what you're doing is you're actually losing more gravel than you have coming in. So you have to make sure you establish that in this problem. You want to say that g of 5 equals 98.141 tons. However, let me actually pause real quick. I'll type this out. Okay, we're back. 98.141 tons are arriving. However, the plant produces 100 tons of gravel per hour. Therefore, the amount of unprocessed gravel is decreasing at time equals 5. So make sure you guys put that in. Make sure you guys consider that 100 tons of gravel per hour being processed. Okay. D. We are looking at what is the maximum amount of unprocessed gravel at the plant during the hours of operation during the workday. Justify your answer. Okay, if you're in period 3, you saw this problem go sideways temporarily here. And so let's go ahead and take a look at this graph one more time here. I'm going to go and adjust my window. Window settings. I'm going to go from 0 to 8 because that's how long the plant is in operation. Now from here, notice how I still can't see the graph. What I'm going to do is I'm going to go to Window again, and I'm going to go to Zoom Fit. So you see how I have my cool cosine graph now. Cool. So the blue function here is what is the rate at which gravel is being processed, rather the rate at which the gravel is incoming into the plant, getting ready to be processed. I'm going to graph yet another function. I'm going to graph y equals 100 because that is going to tell me how much graph is being processed within 0 to 8. And so that's just a constant rate. They told us that. And so hopefully it makes sense that right before this point of intersection here, there is more gravel coming in than there is leaving. And then after whatever this point of intersection is, there's going to be more gravel leaving than coming in. So hopefully it'll make sense that at this point of intersection is going to be where the most gravel occurs. Okay, let's find out this point of intersection. And actually, even if the point of intersection having the most amount of gravel doesn't make any sense, don't worry, we will explain that in a second. So I'm going to find the lower bound, I'm going to find the upper bound. My my point of intersection is 4.92. Now, I have just installed this program, so I have not yet changed the settings of that. You see how it says float 6? I just want it to go to float. Make default. Yes, apply them to Scratchpad. And I probably have to redo this over. I'm going to delete that. So let me do that one more time here. Oh no. Okay, well anyway, if you have yours on float, it will not be 4.92. It will be something a little bit different. It's actually 4.92348, which is what we'll write down. It's not a big deal. So I'm going to go back to here, and I'll go back to my screen also. And so when we talk about the maximum amount of unprocessed gravel within the hours of operation, what we're really dealing with is actually an optimization problem. So I want to look at how much gravel how much gravel when time equals 0, which is when the plant first opens. Time equals 4.9238, and then when time equals 8. So let me just go and explain these real quick. Time equals 0 is when the shop first opens. How much gravel is present, or how much unprocessed gravel is present. About almost a little less than 5 hours into the plant's operation, how much gravel is present, and then at 8 hours, right as soon as the plant is about to close down, how much gravel is present. So what I'm going to do is I'm going to go ahead and integrate the function from 0 to some generic t. Actually, no, let me give myself some more space here. I'm going to integrate the function from 0 to some generic time. This time is going to be switched out with a 0, a 4.9238, and an 8 when I integrate this function 3 times. Now I'm going to integrate how much gravel is coming in. Now in period 3, this is where I kind of lost it. I completely forgot that 100 tons of gravel are leaving per hour. So we got to make sure that we know to include this. And this is why some of us got really large numbers as part of our answer. Now, when we talk about how much unprocessed gravel is at the plant, that is different than how much unprocessed gravel is arriving at the plant. So if we just want to talk about how much gravel is at the plant, we have to consider how much gravel we started out with in the beginning. Now, they told us that in the beginning of the problem. They said that at time equals 0, the plant has 500 tons of unprocessed gravel. So right after my integral, I'm going to add 500 after that. So once I do this into the calculator, you'll see that the answers are going to be 500, because at time 0 you have 500. What you'll get here is you will get 635.376, and then what you'll get here is you will get 525.581. Again, how I got those was I integrated from 0 to 0 for the first one. For the second one, I integrated from 0 to 4.9238 in the calculator. Got that. And then I integrated from 0 to 8 of the same function. Every single time I added 500 after the fact. So this is where your maximum occurs. So justify your answer. So we want to justify the answer by saying, let me go ahead and pause real quick. All right, you want to justify it by saying the maximum amount of gravel occurs at t equals 4.9238 hours of operation. The other pieces of the justification actually occur from your work right here, because you tested the endpoints, which is one of the steps in an optimization problem, and you also tested where the maximum occurred. So there you go. That is number 151. Okay, question 2. It says, a particle moves along a straight line for that interval from 0 to 5. The velocity of the particle is given by that function, and the position of the particle is given by s of t, and it is known that s of 0 equals 10. We need to find all values on the interval at which the speed of the particle is 2. Okay, hang on for a second. Let me go and just input this into the calculator here. So I'm going to go back to this calculator. It looks like it's running away from something. I'm going to go ahead and delete all this stuff. Let's see here. Okay, let me pause real quick. Okay, so check this out. Here is my function right here. I put it right here into the graph. And so what they're asking for in the first example here is they're asking for all the values at which, between 2 and 4 at which the speed of the particle is 2. Now you can do this a couple of different ways. If you know you're on the interval from 2 to 4, then what you can do is you can use the solver. Whoops, wrong function here. You can use the solver back here and just say algebra solve, and you can say for when the absolute value, right? And the reason why I'm using absolute value is because they're asking for when the speed of the function is equal to 2. So I can ask for when that happens. Outside the absolute value bar, here we go, is equal to 2, and then comma x, and then boom. Now I get a bunch of different answers here. So what I want to do is I want to scroll over, and I want to keep scrolling over until I get an answer that is between 2 and 4. And so what I have here is I have 0.094, that's not bigger than 2, so I can go to this 3.1 and then this 3.473, and so those seem to be my answers between 2 and 4. So you can write that down. Now I'll show you a different way of doing it in case you're not too convinced. That is actually not how I did it the first time around this problem. So part A simply is on 2, 4, the absolute value of v of t is going to be equals 2 at t equals 3.127 and 3.473. Now you don't have to put the absolute value of v equals 2, you could just say speed. I like to use this just so that they know that I know what I'm talking about. Okay, so if you didn't feel comfortable with this, it's perfectly fine. What I would recommend you do is you go back to your graph, and so remember, when they're asking you about speed, speed is the absolute value of velocity, and what they gave to you in the beginning is the velocity function. And so what you want to do is you probably want to create a new graph, call it f2 of x, and then graph the absolute value of your first function, and then see what that looks like. So you see how, notice, and I'll go ahead and delete the blue graph in a second here, but notice the red graph, it just bounces all of the negative values up to the top. We've studied what absolute value on the outside of the function does. It'll flip all of the negative y values positive. I'm going to go ahead and get rid of the first function. I'm just going to uncheck it for a second here. And then I'm going to also create a new function called 2. And what I'm going to do is I'm just going to set my window from 2 to 4. And then that'll give me the points of intersection. From here, it's just like the last problem. From here, you would go to Analyze Graph. You'd find an intersection here, lower bound, upper bound. Notice how it's 3.13, but for some reason, I just don't have the time to set my graph back to float normal. You guys know that it's going to be 3.127 if you did it in your calculator, and then you would just do the same thing for this side right here. So let's just go ahead and just do it. Intersection once again, lower bound, upper bound, boom. Notice how it's close enough. Honestly, that is not going to be a good enough answer, so you want to make sure that your calculator is set to float normal, and I have no idea why that is not happening here, but anyway, you guys know what I'm doing. Yes, that is what I want. Okay, so now we're going to go back to Scratchpad. Notice how those answers match with the answers that we found here. So the 3.127 and the 3.473. Notice how the answers match up, so we're all good. Okay, let's go to part B. Part B is asking us to write an expression involving an integral that gives us the position s of t. And we're going to use this expression to find the position of the particle at time equals 5. Okay. So that means that I'm going to integrate from 0 to 5 because I want to find the position of the particle at time equals 5. I'm going to integrate the velocity. Now, what that's going to give to me is it's going to give me the position on 0 to 5. Now, what that equals, whenever we do a definite integral, it's going to be the position at 5 minus the position at 0. Okay, so let me go ahead and get rid of the middleman here. So to make this a little more clear, I'm integrating from 0 to 5 of this function. And that is going to give me s of 5 minus s of 0. But at the very beginning of the problem, they told us that s of 0 equals 10. So I can go ahead and get rid of this s of 0. I can go and get rid of this s of 0 and replace it with a 10. So really, what I have here is I have s of 5 minus 10. Now, if I want to find s of 5, I'm going to add 10 to both sides. So what I really have to get s of 5 is I have 10 plus the integral from 0 to 5 of v of t dt, and that's going to give me my position at 5. So from here, the way that gets input into the calculator is actually a little bit different. So let's go ahead and integrate. Shift plus. Shift plus. Okay, I guess not. Menu. Integral. Why isn't it not doing it? Oh, because I'm still up here. Whoops. Okay. Shift plus. Yes, thank you. 0 to 5 of, you know what, I want to go back and activate that graph again. So I'll go back and I'll activate that graph. That way it knows to call upon it, just in case. Okay, so that would be f1 of x dx. Now that's going to give me negative 19.2 something or other. But remember, that was before I added 10 to it. So I'm going to add 10 now. And really what I'm going to get is I'm going to get my position is negative 9.207. So that's what I'm going to write in. So you would say S of 5 is equal to negative 9.207. And that's it. Okay, let's keep going. Part C asks you, find all times t at which the particle is changing direction. Justify your answer. Okay, so we know that a particle is changing position when the signs change. My recommendation is that you would go back to the graph, because setting it equal to 0 would be great. But just because something is equal to 0 doesn't mean it's going to change direction there. You could be dealing with a double root. You could be dealing with something else that might mess up your results. So what I would say is you go back to your velocity curve here. And I would say clean these up a little bit. I would say get rid of the 2. And then also get rid of the absolute value version of the function. And then go back to zoom standard. And then what you want to do is you want to find out where, I'm going to get rid of these two, so goodbye to you and goodbye to you. This is a velocity curve that we're looking at, so hopefully it makes sense that the graph is going to change places here, here, and here. So it looks like in 3 places, but remember, the question's just asking you on 0 to 2 or 0 to 5 where it's changing directions. So it looks like we're only going to switch our window from 0 to 5. So it is only going to change directions twice. So let's find out where that happens. So we go to Analyze Graph, not intersection, sorry. Analyze Graph 0. Lower bound, upper bound. And so, again, my calculator is set to float 6, so you don't want to go off of what I'm doing. Actually, wait a second. This is 3 decimals. Okay, this one works. So that one works, and now I'm going to go ahead and do it one more time. Lower bound, upper bound, and then this 3 point, I'll call it 318. You see how you don't want to follow this one because this one's only rounded to 3 places. So again, in your calculators you will have a slightly different answer. You want to go with the one that you have on your screen. So let's go back and explain this. You know what? I'm going to pause real quick. So your explanation should look something like this. At t equals 0.536, the particle changes from left to right because velocity goes from negative to positive there, vice versa on the second sentence. And I'll be honest, I don't know if the third sentence is necessary, but I just like to be thorough. You know, you never know what what the person's looking for when they're grading your test. So, okay, cool. Let me go and erase some of this stuff up here, because now we're going to finish off this question. They ask you, is the speed of the particle increasing or decreasing at time equals 4? Give a reason for your answer. When we talk about particles speeding up or slowing down, we want to look at both velocity and acceleration. If the signs for velocity and acceleration are the same, then the particle will be speeding up. If they are opposite, then the particle will be slowing down. So I want to look at the velocity at 4, and I want to look at the acceleration at 4. Well, velocity at 4 can be found pretty easily in our cool calculator. So I can go ahead and find f1 of 4, and that's going to equal that number, which is kind of crazy. So that number, it's a negative number. So we can go back and say that velocity at time equals 4 is equal to negative 11.475, or rather 476. We'll round to 3 decimal places. And now to find the acceleration, I'm going to use that cool function we just learned about called derivative at a point. Derivative at a point right here. My value is x, my point is 4, and I'm going to put in f1 of x. And I'm going to hit enter, and I'm going to hit control enter, and that's negative 22 point all that stuff. So negative 22, and I think you guys already know where this is going, 0.296. Whoa, 0.296. And so, sorry about that little craziness happening there. I have no idea what happened to the screen. Anyway, okay, so regardless of the numbers, they're both negative. So you want to justify this by saying, hold on, that both velocity and acceleration are negative, therefore the particle is speeding up at time equals 5. Cool. Let's move on to the next one. Let's do some revolutions of solids and areas and volumes and more and more and more cool stuff. So this is question 3. Let R be the region enclosed by that graph and y equals 4. Here's the picture for you. And so they want you to find the volume of the solid when R is rotated about the horizontal line y equals negative 2. So here's what we're going to do. I got my graph put into here. I'm going to make another function called y equals 4. It looks exactly like it does in the picture of the FRQ we're dealing with. And now I'm actually going to go ahead and put in a line y equals negative 2. So now, what I'm going to be doing is I'm going to be taking these two functions, the area between them, which is R, the region R they're talking about, and I'm going to rotate it around this line right here. Ooh, it even creates those arrows. Cool. So I'm going to rotate this area here around this line. So here's how I need to set this up. What I need to do is I need to imagine if I was to rotate this area, this region, around a line like this. It involves me finding the area of that region. So that is going to be the integral from 0 to, well, I need to find my points of, my limits of integration. So I'm going to assume that's 0, but let's not be too hasty here. Let's go ahead and go back, and I'm going to find out where those two functions intersect each other. So I'm going to go ahead and use my solver. And I'm going to say f1 of x equals 4, comma x. I'm going to hit enter, 0, and at 2.3. So you could have actually done that by hand. It's actually not that hard. So to find the limits of integration, let me see here. Where's my screen? So it's going to go from 0 to 2.3. And now, from the perspective of this y equals negative 2, the uppermost function is going to be this y equals 4. So I'm going to say that it's going to be 4 squared. Now I'm leaving myself some space on purpose here. And I'm going to subtract the function, because the function is the inner or the lower bound function. And that's going to be dx. Now, a couple things before we move forward that I forgot to mention. We know that it's a dx integral because I'm rotating it about something parallel to the x-axis. Okay? And now, the reason why I left myself space here is because when I find the areas under these curves, it's the area between the function and the x-axis. Okay, so if I just left it at 4, then I'd be getting a lot less area than I need. So what I need is I need to account for this distance, and you can't see that, for this distance right here. And so the way I do that is I add 2 to both functions, because I need to account for the extra space that I need to account for this revolution here. So from here, I just punch that into the calculator. And at this point, I'm going to assume you guys know how to do that into the calculator so I can move this a little bit faster. I'm going to get 98.868. Yeah, that's just integration in the calculator. That's all there is to it. That's part A. Part B region R is now the base of a solid for each cross-section perpendicular to the x-axis. So that tells me, perpendicular to the x-axis, that tells me that this is a dx integral yet again. It's an isosceles right triangle with a leg in R. The leg in R is the most important part right here. Find the volume of the solid. Okay. I'm going to go ahead and give you the answer first, and then I will, what the heck? And then I will explain why the coefficient on the outside is what it is. So, let me check and see if I'm still recording. Am I still recording? Good. Okay. Sorry. Screen blacked out there for a second. Okay. I'm going to throw a 1/2 on the outside, and I'm still going to integrate from 0 to 2.3. And now I'm going to subtract the 2. And then dx. And that is going to equal whatever my answer is. Now, how did I do that? Well, one, you can commit the 1/2 to memory if you want. Personally, I never do. And so the way I see it is, if I'm looking at the base of this region, and it's perpendicular to the x-axis, the triangles that I'm looking at that are protruding out of this region are the bases of those triangles, which is the leg of the isosceles triangle, is determined by the area between the two curves. That is how I got 4 minus f of x, because 4 is the top function, f of x is the bottom function, and the bases will be determined by the distance between the functions. That's how I did that. Now, how did I get the 1/2? A number of different ways you could do that. Well, we know that the area of a square is base times height. And in this case, the base and the height are equal. Now, if I make this an isosceles right triangle, what I'm doing is I am cutting off this half of the square. So whereas a square's area is going to be base times height, or base squared, the area of the of the triangle that's isosceles right triangle is going to be 1/2 of that. Where 1/2 plays the role out here, the base is determined by the 4 minus f of x squared on 0 to 2.3. Okay, cool. So once you put that into your calculator, you will get 3.574. And I just realized that I pasted this problem into the wrong area of the screen, so I need to finish this at the top of the problem here. So the vertical line x equals k divides R into two regions with equal areas. Okay, so let me go ahead and just draw this out here. I don't really know where it's going to be, but I'll go ahead and just draw it right here. It says, write but do not solve an equation involving integral expressions whose solution gives you the value of k. So we know that that if the line x equals k splits the areas in two, then that means that the left side of the integral is going to equal the right side of the integral. So really, this is one of the easier questions. You just have to set two integrals equal to each other and make sure that they involve the value of k, and that somehow those two integrals will equal each other. So here's how you do it. You're going to integrate from 0 to k, and you're going to integrate the function. That's just the area between two curves on 0 to k. And then you're going to make sure that that equals k to 2.3 of the same function. And that's all there is to it. You have the left half of the function equaling the right half of the function. And that's all there is to it. Okay, let's trim some grass. Alright people, it is time for the last problem. Grass clippings are placed in a bin where they decompose from 0 to 30. The amount of grass clippings remaining in the bin is modeled by the function listed right here, where a of t is measured in pounds and t is measured in days. Find the average rate of change over the interval 0 to 30. Indicate units of measure. Make sure you indicate units of measure. It is worth a point. From 0 to 30, well, the average rate of change is found by getting the slope of the line. Now, I have found out how to get more decimals into the graph, so it's all good. Okay, cool. So average rate of change is really just slope of the line, from Algebra 1. So if we just kind of said, okay, well, a of 30 minus a of 0 all over 30 minus 0, and punch that into our calculator, we would get what we need. So I'm going to say f1 of 30 minus f1 of 0, and I'm going to close off those parentheses, and if I divide that by 30, I get that answer. So let's go ahead and see what that is. It is, we get negative 0.197 pounds per day. Now, they don't ask you to justify or interpret the meaning of the value in the context of the problem, unlike B. So you are actually safe with this answer right here. Okay, now that is an A. Okay, let's take a look at B. B is asking, find the value of A prime at 15. Using correct units, interpret the answer. Well, A prime at 15, that's our good old friend, derivative at a point. So if we went back and we went to menu, calculus, derivative at a point, value is 15, and we typed in f1 of x, we would get negative 0.1635. So if we're going to round to 3 decimals, we're going to say that a prime at 15 is going to equal negative 0.164. So we can say, therefore, let me pause this real quick so I can type out the answer. Bam! The amount of grass clippings is decreasing at a rate of 0.164 pounds per day when t equals 15. There was some talk about using the word decomposing. Whatever floats your boat on that one. I mean, I just want you to be careful with what you use. I try to just keep it to increasing, decreasing. That way, you know for sure, that you are actually nailing the answer in the context of the calculus. So, but whatever makes you happy. C says, find the time t for which the amount of grass clippings in the bin is equal to the average amount of grass clippings in the bin over the time interval 0 to 30. Now, we talked about this in class. If I wanted to find out how much grass was remaining in the bin, I would integrate from 0 to 30 of a of t dt. But that's not what they're asking for. They want the amount of grass clippings in the bin being equal to the average amount of grass clippings in the bin on this interval. So I need to multiply this by 1 over 30 because this is an average value problem. Okay? So now, I'm going to go ahead and integrate this function right here. So I'm going to get the integral from 0 to 30 of f1 of x dx. Now, every time I do this, I always end up in trouble. So I'm going to go ahead and actually just go ahead and multiply this by 1 over 30 on the outside here. I always end up in trouble whenever I do some kind of operation after the fact. So boom. So I get 2.7526. So 2.752635. So let me write that down. That equals 2.7526. Whoops. 2.7526 3510. 351077. Okay, this is telling me how much grass is in the bin, but remember, they're not asking for that. They want me to find out when this number is equal to the average amount of grass clippings in the bin. So I need to take this number and I need to set it equal to a of t in order to find out the time at which this is true. So when you do that, you're going to punch it into your calculator. You're going to say calculator solve, or rather algebra solve, sorry. 2.7526351077 is equal to f1 of x, comma x, hit enter, and that is going to give you your answer. So when time is equal to 12.415, that is when the average amount of grass clippings in the bin is equal to the average amount on that time period. Okay, part D. For any t greater than 30, L of t, which is the linear approximation to A at time equals 30, is a better model for the amount of grass clippings remaining in the bin. We are going to use this line called L of t to predict the time at which there will be 0.5 pounds of grass clippings remaining in the bin, and we have to show our work that leads to the answer. Okay. It says to predict the time. So hopefully it makes sense that we are solving for t, and we are going to use linear approximation, which means I need the equation of a line. The equation of a line in point-slope form is y minus y1 equals m times x minus x1. Now, you already have a couple of these pieces real quick. What you have is you have L of t, which is going to be like y, minus your y1. So let's go ahead and find out what y1 is. It says here, we're trying to use the linear approximation to A at time equals 30. So hopefully it makes sense that your x coordinate, or your t coordinate of this one, is going to be 30, comma. And then your y coordinate, or your A coordinate, is going to be A of 30. Now, this is just a representation of what happens when you take 30 and plug it into this function. I don't really know what this is. All I know is that I'm going to push it into the calculator, and it's going to do it. So I can say that 30 comma A of 30 are going to be my two coordinates that I use in this linear approximation. So I'm going to say L of t, which is like y, minus A of 30 is going to equal whatever slope I'm dealing with times t minus 30, right? x1 being 30, t being x. Now all I need to do is figure out my slope at 30. Well, that's easy. That's a prime of 30. So this is my equation for my linear approximation right here. So now all I have to do is just figure out what each of these pieces are. So what I'm going to do is I'm going to say that A of 30, I've already punched that into the calculator, that is 0.7822928. A prime at 30 is going to be negative 0.055976. And remember, I'm solving for t because it's asking us to find out when that happens. Well, L of t is the resulting amount of grass clippings left. This is my 0.5. So all I need to do is figure out when all this is true. So if I subtract these two, I'm going to get negative 0.282928, and that's going to equal negative 0.055976 times t minus 30, and I'll solve that in the calculator for t. And so let's see what that looks like. Menu. Algebra. I love this solve function, by the way. It's cool. Anyway, negative 0.282928 is equal to negative 0.055976 times x minus 30, comma x. And I hit enter, and I'm crossing my fingers right now. 35.05. That is what they are looking for. So you would say at t equals 35.054, the amount of clippings remaining, that is supposed to say remaining, will be 0.5 pounds. Cool. Those are your FRQs. Good luck studying. And actually, this reminds me, I gotta go mow my lawn, so I will see ya.